The question of how atoms came from nothing is deeply intertwined with some of the most fundamental concepts in physics, cosmology, and the philosophy of existence. To explore this subject fully, we need to travel back to the very beginning of time, to the origins of the universe itself, and move forward through the processes that led to the formation of atoms and matter. This journey will take us through the realms of quantum physics, general relativity, particle physics, and cosmology, touching on ideas that challenge our understanding of reality. To begin, we must first address the concept of nothingness. In everyday language, we think of nothing as the absence of everything, no matter, no energy, no space, and no time. However, in the context of physics and cosmology, the concept of nothing is more complicated. When physicists speak of nothing, they often refer to the quantum vacuum, a state that, while devoid of matter, is still a seething sea of energy and virtual particles fluctuating in and out of existence. Thus, the idea of atoms emerging from nothing is not about atoms popping into existence from a pure void, but rather about how complex structures formed from the fundamental building blocks of reality, which may have themselves emerged from a state that we approximate as nothing. The story of atoms begins with the Big Bang, the event that marks the birth of our universe. Approximately 13.8 billion years ago, all of space, time, energy, and matter were condensed into an extremely hot and dense singularity. At this point, physics as we understand it breaks down, and describing what happened before the Big Bang is beyond our current knowledge. Some theories suggest that the universe could have arisen from quantum fluctuations in a pre-existing multiverse or from a state of quantum nothingness, where even the concept of time has no meaning. According to the prevailing view, however, the Big Bang represents the moment when time, space, and matter as we know them began. In the first moments after the Big Bang, the universe was an incredibly hot and dense plasma of energy. Matter, as we know it, did not yet exist. The temperatures were so extreme, on the order of trillions of degrees Kelvin, that even elementary particles like protons and neutrons could not form. Instead, the universe was filled with a mixture of fundamental particles, including quarks and gluons, which interacted in a chaotic manner. As the universe expanded and cooled, it entered a phase known as baryogenesis. This period saw the creation of the baryons, which are particles like protons and neutrons that make up atomic nuclei. However, not all particles survived this process. For every particle of matter created, an antiparticle of antimatter was also formed. When matter and antimatter meet, they annihilate each other, converting into pure energy. Somehow, though, there was a slight imbalance in the number of matter particles and antimatter particles, with about one extra matter particle for every billion pairs of matter and antimatter. This tiny excess of matter over antimatter is what allowed the universe to have any matter at all once the rest had annihilated and vanished into energy. The next significant milestone in the formation of atoms was nucleosynthesis, which took place just a few minutes after the Big Bang during a period known as the Big Bang nucleosynthesis. By this time, the universe had cooled enough for protons and neutrons to come together and form the first atomic nuclei, but it was still too hot for these nuclei to capture electrons and form neutral atoms. During this period, the only elements that could form were hydrogen, helium, and trace amounts of lithium and beryllium. These elements are known as the primordial elements, and they account for most of the ordinary matter in the universe even today. However, the universe remained too hot and energetic for electrons to bind to these nuclei and form complete atoms. Instead, the universe was a plasma, a hot, ionized gas of free electrons and nuclei. It wasn't until about 380,000 years after the Big Bang, during an era called recombination, that the universe cooled enough for electrons to be captured by atomic nuclei, creating the first neutral atoms. Most of these atoms were hydrogen, the simplest and most abundant element in the universe, consisting of one proton and one electron. This marked the end of the photon-baryon soup era and the beginning of the universe as we know it, with matter and radiation separating, allowing light to travel freely through space for the first time. This light, stretched and cooled over billions of years, is what we observe today as the cosmic microwave background radiation, a faint afterglow of the Big Bang. Even though hydrogen and helium were the only elements formed in significant quantities during the Big Bang, they were just the beginning. Heavier elements like carbon, oxygen, and iron, the elements essential for life, were formed later inside stars through a process known as stellar nucleosynthesis. When stars run out of hydrogen to fuse in their cores, they begin fusing helium into heavier elements. In the most massive stars, this process continues, producing heavier and heavier elements until iron is formed. However, the process stops at iron, as fusing iron into heavier elements requires more energy than it releases. These heavy elements were dispersed throughout the universe when massive stars exploded in supernovae, releasing their material into space. Over time, this material coalesced into new stars, planets, and eventually the atoms that make up everything we see around us, including life itself. The concept of atoms arising from nothing also touches on the strange world of quantum mechanics, where particles can emerge spontaneously from the vacuum due to quantum fluctuations. In the quantum realm, even empty space is not truly empty. Instead, it is a dynamic environment filled with energy fields. Virtual particles can pop into existence for a fleeting moment before disappearing again. This phenomenon is a direct consequence of the uncertainty principle, which states that certain pairs of physical properties, like energy and time, cannot both be precisely known at the same time. As a result, energy can borrow existence for a brief time, allowing particles to appear out of the quantum vacuum. One of the most mind-bending aspects of this process is that it suggests the universe itself could have emerged from a quantum fluctuation. The idea that something can come from nothing is supported by some interpretations of quantum mechanics, where the vacuum state is not a state of absolute emptiness but a rich and complex structure that allows for the spontaneous creation of particles and fields. This has led some scientists to propose that the entire universe may have originated from a quantum fluctuation in a vacuum, essentially emerging from nothing, in the conventional sense. As we delve deeper into this idea, we must also confront the role of dark matter and dark energy, which together make up about 95% of the universe's total energy content. Dark matter is a mysterious form of matter that doesn't interact with light, making it invisible, while dark energy is a form of energy that is driving the accelerated expansion of the universe. Although atoms make up only a small fraction of the total content of the universe, they are crucial in shaping the structures we observe, such as galaxies and stars. The interplay between ordinary matter, atoms, dark matter, and dark energy is fundamental to the large-scale structure and evolution of the universe. While we don't fully understand what dark matter and dark energy are, we know that they played a crucial role in the formation of atoms and the subsequent development of cosmic structures. Dark matter, which interacts gravitationally with ordinary matter but not electromagnetically, helps aid the formation of galaxies by creating dense regions of gravitational pull. These dense regions acted as cosmic wells that drew in hydrogen and helium gas, enabling stars to form and eventually heavier elements through stellar processes. Without dark matter, the universe would likely look very different, and the conditions necessary for atom formation and star formation may not have existed. But what about the concept of nothing? To truly grapple with this, we need to explore the role of the vacuum in modern physics, particularly in the framework of quantum field theory. In quantum field theory, every particle is understood as an excitation or disturbance in a corresponding field that permeates all of space. Even in the absence of particles, these fields still exist, fluctuating and interacting in subtle ways. This concept of the quantum vacuum is quite different from the classical notion of an empty void. In fact, the quantum vacuum is an incredibly dynamic environment, one in which particles can temporarily pop into and out of existence due to these fluctuations. A particularly interesting phenomenon related to the quantum vacuum is the Casimir effect, which provides experimental evidence that the vacuum is not truly empty. The Casimir effect occurs when two uncharged, parallel plates are placed very close together in a vacuum. Because of quantum fluctuations, virtual particles continuously appear and disappear around the plates. However, fewer fluctuations can occur between the plates because of the restricted space. This difference in fluctuations creates a measurable force that pushes the plates together. The Casimir effect illustrates how quantum fluctuations, even in a seemingly empty space, can give rise to real, observable phenomena. The possibility that the universe emerged from a quantum vacuum aligns with some versions of inflation theory, which proposes that the universe underwent an extremely rapid expansion in the first fraction of a second after the Big Bang. According to this theory, quantum fluctuations in a pre-existing vacuum gave rise to a tiny, dense, and hot region of space that underwent exponential expansion, leading to the universe we observe today. Inflation explains several puzzles in cosmology, such as why the universe appears so uniform and why regions that should not have been in causal contact with one another still exhibit similar properties, like the cosmic microwave background radiation. Inflation also offers an explanation for how the seeds of structure, such as galaxies, arose from the early universe. During inflation, tiny quantum fluctuations in the density of matter were stretched to cosmic scales. These fluctuations later became the gravitational wells into which matter, primarily hydrogen and helium, collapsed to form stars and galaxies. In this sense, quantum fluctuations from nothing ultimately gave rise to the complex structures we observe in the universe today, including the atoms that make up stars, planets, and life itself. However, the question remains, how did the universe's fundamental forces and particles arise from the energy of the early universe? The answer to this lies in the process of symmetry breaking. In the earliest moments of the universe, when temperatures were unimaginably high, the fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were likely unified into a single force. As the universe expanded and cooled, these forces broke apart, each becoming distinct. This process, known as symmetry breaking, also gave rise to the different particles that make up the universe today. The most well-known example of symmetry breaking is the Higgs mechanism, which is responsible for giving particles mass. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed a crucial part of the Standard Model of particle physics. According to the Higgs mechanism, a field, known as the Higgs field, permeates the entire universe. Particles acquire mass by interacting with this field, much like how an object moving through water experiences resistance. Without the Higgs field, particles like quarks and electrons would have no mass, and atoms as we know them would not exist. The formation of atoms was not a one-time event confined to the early universe. It is an ongoing process, continually shaped by stellar evolution, cosmic collisions, and even human activity. Stars are the engines of atomic creation, forging new elements in their cores through nuclear fusion. When a massive star exhausts its nuclear fuel, it often explodes in a supernova, scattering the heavy elements it created into space. These elements become part of interstellar clouds, which can eventually collapse under their own gravity to form new stars, planets, and in some cases, life. Thus, atoms that were once forged in the hearts of stars billions of years ago now reside in the cells of your body. But atoms are not static entities. They constantly interact, bond, and recombine to form molecules, which in turn make up the substances we see around us. Atoms also decay over time. For instance, certain isotopes of elements are unstable and will decay into other elements through radioactive processes. This decay is an important source of energy on Earth, powering geothermal activity and contributing to the warmth of the planet's core. The radioactive decay of elements like uranium also provides a critical dating tool for scientists studying the history of the Earth and the universe. As we move from the cosmological to the quantum scale, the behavior of atoms becomes increasingly strange. Quantum mechanics governs the behavior of particles at the atomic and subatomic levels, where particles like electrons do not behave like solid objects but rather as probabilistic wave-like entities. Electrons, for example, do not orbit the nucleus of an atom in the way that planets orbit the Sun. Instead, they exist in clouds of probability, only occupying well-defined regions when they interact with other particles or are measured. One of the key insights of quantum mechanics is the principle of superposition, which states that particles can exist in multiple states simultaneously. An electron in an atom, for example, can exist in a superposition of energy levels until it is observed, at which point it collapses into one definite state. This phenomenon has profound implications for our understanding of reality and challenges our classical intuitions about how the world works. Another essential concept in quantum mechanics is entanglement, where two or more particles become linked in such a way that the state of one particle is directly related to the state of another, no matter how far apart they are. If two particles are entangled, measuring the state of one will instantly determine the state of the other, even if they are separated by vast distances. This spooky action at a distance, as Albert Einstein called it, has been experimentally confirmed and is now a cornerstone of quantum theory. It suggests that the fabric of reality is interconnected in ways that we do not fully understand and raises intriguing questions about the nature of atoms and their interactions. As we ponder the origins of atoms and how they emerged from nothing, it's worth reflecting on the philosophical implications of this question. Some physicists and cosmologists argue that the universe, and everything in it, is the result of a random fluctuation in a quantum vacuum, implying that there is no deeper reason or purpose behind existence. Others see the fine-tuning of the universe's physical constants, such as the strength of the gravitational force or the charge of the electron, as evidence that our universe may be one of many in a vast multiverse, with different physical laws governing each one. Still, others take a more metaphysical approach, speculating that the emergence of atoms, life, and consciousness could point to some underlying principle or intelligence guiding the cosmos. The formation of atoms from nothing is a multifaceted question that touches on the deepest mysteries of existence, from the quantum fluctuations that may have sparked the Big Bang to the nuclear processes inside stars that continue to forge the elements of the universe. Atoms are the building blocks of matter, but their existence and behavior are governed by principles that often defy our everyday understanding of reality. The universe, in all its complexity, appears to have emerged from a state that was, in many ways, indistinguishable from nothing. Yet it has given rise to the rich tapestry of matter, energy, and life that we see today. This journey from nothingness to the intricate structures of atoms and galaxies is one of the most profound stories science has to offer. The journey from the concept of nothing to the formation of atoms is far more complex than the surface of our everyday reality reveals. As we continue this exploration, we must dive even deeper into the profound scientific and philosophical implications of the origin of everything. The idea that something could come from nothing challenges both our intuitive and classical understanding of physics and reality itself. Yet, in the language of quantum mechanics and cosmology, such a concept is not only plausible but appears to be a natural outcome of the universe's fundamental laws. Theories of the universe's beginning, such as the Big Bang, suggest that all of space, time, and energy were once compressed into an infinitesimally small, hot, and dense state known as a singularity. This point contained everything, all energy and potential for matter, in a form that transcends ordinary physical description. In a state so extreme, the known laws of physics break down, making it difficult to fully comprehend what exactly existed before the Big Bang or what nothingness might have been like. However, one of the key ideas of cosmology is that the Big Bang did not emerge in space and time, but rather space and time themselves began with this event. This idea that time itself had a beginning is deeply counterintuitive, leading us to ponder whether nothingness could even exist before time or space. In quantum cosmology, the vacuum energy of space is viewed not as true emptiness but as a seething, active background filled with potential for fluctuations. These fluctuations are not like the classical idea of randomness but are instead rooted in the uncertainty principle of quantum mechanics. This principle, formulated by Werner Heisenberg, states that certain pairs of physical properties, such as position and momentum, or energy and time, cannot both be measured with perfect precision. In other words, there is a fundamental fuzziness at the heart of quantum systems that gives rise to these fluctuations, even in a vacuum. These vacuum fluctuations could be the very seeds that led to the creation of all the matter in the universe. Inflationary cosmology, a leading theory, suggests that in the fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. During this inflationary period, quantum fluctuations in the fabric of space-time were blown up to macroscopic scales, seeding the tiny density variations that would later grow into galaxies, stars, and planets. The vacuum energy driving inflation would have created regions of lower and higher density, which helped determine the distribution of matter as it cooled. These fluctuations could be seen as the first steps in the creation of the atoms that would eventually coalesce into the structures of the universe. Once the universe began to cool after inflation, the formation of elementary particles began in earnest. During the first few minutes of the universe's history, conditions were just right for the creation of the lightest elements, a process known as Big Bang nucleosynthesis. At this stage, the universe was filled with a hot, dense soup of protons and neutrons, the building blocks of atomic nuclei. These particles were initially in thermal equilibrium with the intense radiation that permeated the early universe. As the universe continued to expand and cool, nuclear reactions began, fusing protons and neutrons into the first atomic nuclei, primarily hydrogen, helium, and small amounts of lithium and beryllium. Big Bang nucleosynthesis was a brief but critical period in cosmic history, lasting only about 3 minutes, but it set the stage for everything that would follow. By the end of this epoch, the universe had cooled too much for further nuclear reactions to occur, and the formation of heavier elements would have to wait until stars formed billions of years later. At this point, the universe was still a hot plasma of charged particles and photons. It wasn't until roughly 380,000 years later that the universe cooled enough for neutral atoms to form in a process known as recombination. During recombination, electrons finally became bound to nuclei, and the universe transitioned from an opaque plasma to a transparent cosmos filled with neutral hydrogen and helium atoms. This event allowed photons to travel freely through space for the first time, and the light from this period is still visible today as the cosmic microwave background radiation. The era of recombination was a critical turning point because it marked the end of the early universe's chaotic, high-energy environment and the beginning of a universe governed by gravity and electromagnetism, forces that would shape the large-scale structures we see today. Neutral atoms could now form clouds of gas that, under the influence of gravity, would begin to collapse and coalesce into the first stars and galaxies. But while the creation of atoms from nothingness may seem miraculous, it is only the beginning of a much longer journey. As the universe continued to evolve, stars acted as cosmic factories, synthesizing heavier elements in their cores through the process of nuclear fusion. Fusion occurs when the nuclei of lighter atoms, like hydrogen, combine under immense pressure and temperature to form heavier elements like helium, carbon, and oxygen. In massive stars, fusion can continue all the way up to the production of iron. However, beyond iron, fusion requires more energy than it releases, and so it cannot continue in the normal life cycle of a star. When massive stars exhaust their nuclear fuel, they undergo a dramatic collapse, often resulting in a supernova explosion. These cataclysmic events are responsible for creating elements heavier than iron, including gold, uranium, and other rare and heavy elements. Supernovae are also responsible for dispersing these elements into space, enriching the interstellar medium with the building blocks needed to form new stars, planets, and eventually, life. As we contemplate the origin of atoms and how they came from nothing, it's important to consider that the creation of the universe was not a one-time event confined to a distant past. The universe is still evolving, and new atoms are being created even today. For instance, in stars, nuclear fusion is an ongoing process that continues to generate new elements, while in laboratories on Earth, scientists are constantly exploring ways to create new forms of matter through particle accelerators and nuclear reactors. The idea that atoms came from nothing invites a deeper philosophical question: what is the nature of existence itself? The famous quote from the German philosopher Gottfried Wilhelm Leibniz, "Why is there something rather than nothing?" captures the essence of this mystery. While modern physics provides a framework for understanding how the universe evolved from a hot, dense state to its current form, the question of why there is something at all, why the universe exists rather than not existing, is still open to debate. Some philosophers and scientists argue that the existence of the universe is simply a brute fact, something that needs no further explanation. Others posit that there must be some deeper principle, or cause behind the existence of the universe. One of the most intriguing ideas in modern cosmology is the concept of the multiverse. According to some interpretations of quantum mechanics and string theory, our universe may be just one of an infinite number of universes, each with its own physical laws and constants. In such a scenario, the existence of atoms in our universe could be a consequence of the specific conditions that happen to arise in this particular universe. Other universes might have different physical laws, where atoms either cannot form or behave in entirely different ways. The multiverse hypothesis provides one possible answer to the question of why the universe appears to be fine-tuned for the existence of matter, atoms, and life. While the idea of a multiverse remains speculative, it highlights the profound implications of asking where atoms, and by extension, everything we observe, came from. Whether through quantum fluctuations, vacuum energy, or the process of inflation, the emergence of atoms from nothing challenges us to rethink our understanding of reality, pushing the boundaries of both science and philosophy. The journey of how atoms came from nothing is not just a story of particles and forces. It is a narrative that touches on the very origins of existence. The atoms that make up the universe were born out of the extreme conditions of the early cosmos, guided by fundamental physical laws that govern everything from the smallest subatomic particles to the largest galaxies. The formation of atoms is a testament to the power of physics, but it also raises profound questions about the nature of existence itself, questions that may never have simple answers, but which continue to inspire our search for knowledge. As we delve further into the cosmic origins of atoms, we find ourselves exploring concepts that not only intersect with physics but also stretch into philosophical and metaphysical realms. The creation of atoms from nothing invites us to confront the boundary between what is scientifically knowable and what remains speculative or mysterious. While the Big Bang Theory, quantum fluctuations, and inflationary models offer frameworks for understanding the emergence of matter, they don't fully explain why these processes occurred or why the laws of physics themselves exist in the first place. This is a frontier where the scientific quest for answers encounters the profound and often unsettling question of existence. The existence of atoms, with their intricate internal structures of protons, neutrons, and electrons, is predicated on forces and constants that are delicately balanced. The electromagnetic force, for instance, holds electrons in orbit around atomic nuclei, while the strong nuclear force binds protons and neutrons together within the nucleus. Without these forces, or if they were only slightly different in strength, atoms as we know them could not exist. This fine-tuning of the universe, where the physical constants appear to be precisely set to allow for the formation of matter and life, raises questions about whether this delicate balance is a random outcome or the result of some deeper principle or design. One perspective is that the fine-tuning of the universe is simply a coincidence, a lucky roll of the cosmic dice. In a multiverse scenario, where countless other universes may exist with different laws of physics, it's conceivable that most universes would not be hospitable to matter or life. In this view, we just happen to live in one of the rare universes where the physical constants are set just right. This interpretation is often called the anthropic principle, which suggests that we observe the universe to be finely tuned because, if it weren't, we wouldn't be here to observe it in the first place. However, the anthropic principle does not fully satisfy those who seek a deeper explanation for the origin of atoms and the universe. It merely shifts the question, why does the multiverse, or the specific conditions that gave rise to our universe, exist at all? This brings us back to the fundamental question of whether there is a reason for existence, or whether it is a brute fact, an inexplicable reality that simply is. As we look deeper into the creation of atoms, we must also consider the role of quantum mechanics, the branch of physics that governs the behavior of the smallest particles in the universe. Quantum mechanics introduces the idea of probabilities and indeterminacy into our understanding of nature. At the quantum level, particles do not have definite positions or velocities until they are measured. Instead, they exist in a superposition of possibilities. This strange and counterintuitive aspect of reality suggests that, on some fundamental level, the universe is not deterministic but probabilistic. The random fluctuations in the quantum field that gave rise to the first particles and eventually atoms may be seen as part of this inherent uncertainty in nature. One of the key features of quantum mechanics that may help explain the emergence of matter from nothing is the concept of quantum tunneling. In classical physics, a particle cannot pass through a barrier if it does not have enough energy. However, in the quantum world, particles have a small probability of tunneling through barriers, even if they do not have enough energy in the classical sense. This phenomenon is crucial in many physical processes, including the nuclear fusion that powers stars. Similarly, quantum tunneling may have played a role in the early universe, allowing particles to emerge from the quantum vacuum, even when conditions seemed impossible for such events in a classical sense. Quantum mechanics also suggests that the vacuum of space is not truly empty. Instead, it is filled with virtual particles that constantly pop in and out of existence due to the uncertainty principle. These virtual particles exist for only the briefest moments before annihilating each other, but their fleeting presence indicates that nothingness, at the quantum level, is not a simple void but a dynamic, active state. These quantum fluctuations could be responsible for creating the conditions necessary for the formation of atoms. This process would have been amplified during the inflationary period of the universe, when tiny quantum fluctuations were stretched across vast regions of space, providing the seeds for the formation of galaxies and other large-scale structures. Yet, despite these scientific explanations, the question of how atoms came from nothing is not fully resolved. The idea that something could emerge from nothing challenges not only our scientific understanding but also our deepest philosophical intuitions about causality and existence. Classical physics, rooted in the ideas of Isaac Newton and others, is built on the principle of cause and effect. Everything that happens has a cause. But in the quantum realm, causality appears to break down, or at least it operates in ways that defy our classical intuitions. This raises a profound question. If the laws of quantum mechanics allow for the spontaneous creation of particles from the vacuum, does this imply that the universe itself could have emerged spontaneously from nothing? Some physicists, such as Lawrence Krauss in his book A Universe from Nothing, have argued that the laws of quantum mechanics make it possible for the universe to arise from a state of nothingness. However, this concept of nothing in physics is not the same as the philosophical notion of absolute nothingness. In physics, nothing often refers to the quantum vacuum, a state that is still governed by physical laws and contains potential energy. The idea of absolute nothingness, a complete absence of space, time, energy, and physical laws, remains a much more difficult concept to grasp, and it is unclear whether such a state could even exist or be meaningfully described. As we reflect on the emergence of atoms and the universe, we must also consider the role of time. The Big Bang Theory suggests that time itself began with the birth of the universe. But what does it mean for time to have a beginning? In our everyday experience, time seems to flow in one direction, from the past to the future, governed by the second law of thermodynamics, which states that entropy, or disorder, always increases. But at the moment of the Big Bang, the concept of time as we understand it may not have applied. Before the Big Bang, if such a state can be meaningfully described, there may have been no before, in the way we normally think of it. This suggests that the origin of the universe and the atoms within it is not just a question of matter and energy but also a question of the nature of time itself. One possible way to approach this problem is through the idea of a cyclical, or oscillating universe. In some cosmological models, the universe undergoes cycles of expansion and contraction, with each Big Bang followed by a Big Crunch, in which the universe collapses back into a singularity, only to explode again in another Big Bang. In such a model, the universe has no true beginning or end but exists in an eternal cycle of creation and destruction. While this idea is intriguing, it faces significant challenges, including the fact that the observed expansion of the universe appears to be accelerating rather than slowing down, making a future Big Crunch seem unlikely based on current evidence. Another approach to understanding the origin of atoms and the universe is through string theory, a highly speculative but mathematically rich framework that attempts to reconcile quantum mechanics and general relativity. According to string theory, the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings of energy. These strings exist in multiple dimensions, beyond the 3 dimensions of space and one of time that we experience in everyday life. String theory suggests that the particles that make up atoms, protons, neutrons, electrons, and even quarks, are all different vibrational modes of these strings. In this view, the emergence of atoms from nothing could be seen as the result of the complex interplay of energy and vibration at the most fundamental level of reality. While string theory offers a tantalizing glimpse into the possible deeper structure of the universe, it remains an unproven hypothesis. Nevertheless, it provides one possible framework for understanding how the fundamental forces and particles that make up atoms could arise from more basic principles. As we continue to explore the origins of atoms and the universe, it becomes clear that this is not merely a scientific question but also a deeply philosophical one. The idea that the universe could have emerged from nothing challenges our understanding of existence, causality, and time. Whether we ultimately find a definitive answer to this question or not, the quest for knowledge continues to push the boundaries of human understanding, forcing us to confront the deepest mysteries of the cosmos. The quest to understand how atoms emerged from nothing transcends the boundaries of traditional science, delving into areas where physics meets metaphysics, philosophy, and even theology. As we explore the implications of the birth of atoms and the universe, we encounter not only scientific principles but also questions about the nature of reality, existence, and the fabric of space-time itself. One of the fundamental questions in this discourse is whether nothing can truly exist. Philosophically, nothing is often defined as the absence of anything: no matter, no energy, no space, and no time. However, in modern physics, particularly quantum mechanics, the concept of nothingness takes on a different dimension. The vacuum state in quantum field theory is not an empty void. It is a seething background filled with potential. It is a state where particles can emerge and vanish spontaneously due to quantum fluctuations, suggesting that nothing, in the quantum sense, is a dynamic and active state rather than a static absence. This perspective raises profound implications for the understanding of creation itself. If particles can spontaneously arise from the vacuum, then the universe's birth may not require a prior state of existence, or an external creator. In this view, the universe could indeed be self-generating. This proposition is particularly compelling when considered alongside the idea of the multiverse, where our universe is just one of many, each governed by different physical laws. If there are countless universes, each with different constants and properties, then our universe, capable of forming atoms and life, could be just one possibility among many. In exploring the multiverse concept, we must also confront the issue of empirical verification. While multiverse theories offer elegant solutions to various cosmological problems, they often fall short of providing testable predictions. This lack of empirical evidence leads some physicists and philosophers to question the validity of such theories, positing that a scientifically valid theory should ultimately be falsifiable. Yet, the multiverse invites philosophical discussions about the nature of scientific inquiry itself. It challenges our traditional notions of what it means to understand the universe, expanding the boundaries of inquiry beyond the observable to the potentially unobservable. As we examine the implications of these ideas, we also confront the question of time and causality in the context of the universe's origin. If time began with the Big Bang, then what does that mean for causality? In a universe where time is a product of the very fabric of space-time, the traditional notion of cause and effect becomes complex. Some theories suggest that prior to the Big Bang, conventional ideas about time and causality might not apply. This notion aligns with certain interpretations of quantum mechanics, where events can occur without direct cause and effect relationships, further complicating our understanding of the universe's genesis. In addition to quantum mechanics and cosmological theories, the discussion surrounding the origins of atoms also touches on philosophical interpretations of existence. The question of why there is something rather than nothing has been pondered by philosophers for centuries. Figures such as Martin Heidegger explored the essence of being and existence, grappling with the implications of existence itself. In contemporary philosophy, discussions about existence often involve considerations of consciousness, reality, and the very fabric of the universe. Some philosophical viewpoints suggest that existence may be a fundamental aspect of reality, inherent in the nature of the cosmos itself. From this perspective, the emergence of atoms and the universe might be seen as a natural expression of existence rather than a miraculous event. This viewpoint resonates with certain interpretations of Eastern philosophy, where existence and non-existence are not viewed as binary opposites but as interconnected aspects of a single reality. The relationship between consciousness and the universe also invites exploration. Some theories propose that consciousness plays a role in shaping reality, a notion echoed in various spiritual and philosophical traditions. The idea that conscious observation may influence the behavior of particles is a cornerstone of quantum mechanics, particularly in the observer effect, where the act of measurement alters the state of a quantum system. This has led to discussions about whether consciousness is merely a byproduct of physical processes or if it plays a more fundamental role in the cosmos. The interplay between consciousness and the material world raises profound questions about the nature of existence. Is the universe simply a collection of particles and forces, or is it imbued with meaning, purpose, and consciousness? These questions transcend the realms of empirical science and enter the domain of philosophy and the human experience. Moreover, as we explore how atoms emerge from nothing, we must also consider the implications of our understanding of time. In many cosmological models, time is viewed as a linear progression, moving from the past through the present and into the future. However, theories such as loop quantum gravity suggest that time may not be fundamental but rather an emergent property of more basic processes in the universe. This notion challenges our traditional understanding of time and invites us to reconsider how we perceive change and existence itself. Another area of interest is the relationship between thermodynamics and the universe's birth. The second law of thermodynamics states that in a closed system, entropy, disorder, tends to increase over time. This raises intriguing questions about the early universe and the conditions under which it formed. The Big Bang represents a state of extremely low entropy, where energy and matter were concentrated in a singular point. As the universe expanded, entropy began to increase, leading to the complex structures we observe today. The relationship between entropy and the universe's expansion suggests that the birth of atoms and the evolution of the cosmos are interconnected processes governed by the laws of thermodynamics. As we continue our exploration, it's essential to acknowledge the contributions of different fields to our understanding of the universe's origins. Cosmology, physics, philosophy, and even theology all offer valuable insights into the questions surrounding the emergence of atoms and the nature of existence. This interdisciplinary approach enriches our understanding and highlights the complexity of the questions we are attempting to answer. Throughout this journey, the concept of nothingness remains a central theme. The idea that something can arise from nothing challenges our intuitive understanding of existence and causality. Yet, as we explore the nuances of quantum mechanics and cosmology, we begin to see that nothing may not be as simple as it appears. The vacuum of space, filled with potential and activity, suggests that even in the absence of matter and energy, the fabric of reality is dynamic and alive. Furthermore, as we approach the question of creation from a philosophical standpoint, we encounter various perspectives on existence. Some philosophical traditions posit that existence is an intrinsic quality of the universe, while others argue that it is contingent upon external factors or forces. The interplay between existence and nothingness invites profound contemplation on the nature of reality and our place within it. Ultimately, the journey to understand how atoms came from nothing is a quest that transcends mere scientific inquiry. It invites us to ponder the nature of existence, the fabric of reality, and our relationship with the cosmos. Whether we view the birth of atoms as a result of spontaneous quantum fluctuations, a manifestation of deeper principles of reality, or an expression of conscious awareness, the exploration continues to challenge and inspire us. As we navigate the complexities of these questions, we find ourselves at the intersection of science and philosophy. Each discipline offers unique insights into the nature of existence and the processes that govern the universe. The dialogue between these fields enriches our understanding and fosters a sense of wonder about the cosmos. The question of how atoms came from nothing serves as a profound entry point into the mysteries of existence and the nature of reality. As we unravel the threads of quantum mechanics, cosmology, and philosophical inquiry, we begin to glimpse the intricate tapestry of the universe. The exploration of these ideas not only deepens our understanding of the cosmos but also invites us to reflect on our place within it, a reminder that the quest for knowledge is as much about the journey as it is about the answers we seek. As we delve deeper into the relationship between atoms, energy, and the concept of nothingness, we can also explore the role of forces in the formation of matter. The universe operates under four fundamental forces: gravitational, electromagnetic, strong nuclear, and weak nuclear forces. Each of these forces plays a crucial role in shaping the cosmos and determining how matter interacts at various scales. Initially, during the first moments of the universe, when it was incredibly hot and dense, the forces we recognize today behaved differently. In this extreme environment, known as the Planck epoch, it is theorized that all four fundamental forces may have been unified. As the universe expanded and cooled, these forces separated, leading to the formation of distinct interactions that govern the behavior of matter and energy. The process of symmetry breaking is essential in understanding how this transition occurred, as it set the stage for the structure of the universe as we know it. The electromagnetic force, for instance, is responsible for the interactions between charged particles. It plays a vital role in the formation of atoms, as it governs how electrons interact with the positively charged nucleus. Without the electromagnetic force, atoms would not exist as we know them. Similarly, the strong nuclear force binds protons and neutrons within the atomic nucleus, ensuring the stability of matter. Understanding these fundamental interactions is crucial for grasping how atoms can emerge from the primordial chaos of the universe. Moreover, the weak nuclear force is essential in processes such as beta decay, when neutrons transform into protons, influencing the balance of matter and antimatter in the universe. This transformation is critical for the evolution of elements during stellar nucleosynthesis, which occurs within stars. The intricate interplay between these forces reveals how the emergence of atoms is not merely a random occurrence but a consequence of the fundamental laws governing the universe. As we examine the formation of atoms in more detail, we encountered the concept of nucleosynthesis, the process through which elements are formed from simpler particles. During the first few minutes after the Big Bang, the universe underwent a period of rapid expansion and cooling, allowing protons and neutrons to combine and form the lightest elements, primarily hydrogen and helium. This process, known as Big Bang nucleosynthesis, is a critical step in the development of the universe, as these elements provided the building blocks for more complex structures. Following the Big Bang, the universe entered a phase known as the Cosmic Dark Ages, when no stars or galaxies existed, and the universe was filled with neutral hydrogen gas. Over time, regions of higher density began to collapse under the influence of gravity, leading to the formation of the first stars and galaxies. In these early stars, nuclear fusion reactions transformed hydrogen into helium and other heavier elements, a process that would eventually create the rich tapestry of elements we find throughout the universe today. Stellar nucleosynthesis plays a vital role in the cosmic cycle of matter. Stars forge heavier elements through nuclear fusion in their cores, releasing immense energy in the process. When massive stars exhaust their nuclear fuel, they undergo supernova explosions, dispersing these newly formed elements into the interstellar medium. This material then becomes part of the gas and dust clouds from which new stars and planets form. Thus, the atoms that make up our bodies and the world around us are the remnants of ancient stars, a testament to the interconnectedness of the universe. This cyclical nature of matter, from the birth of atoms in the cosmos to their eventual return to the stellar furnace, underscores the dynamic processes at play in the universe. It also raises profound questions about our origins and the continuity of existence. If we are made of star stuff, as Carl Sagan famously stated, then the atoms within us are not merely remnants of an ancient past. They are active participants in the ongoing story of the universe. Furthermore, The processes that govern the formation and transformation of atoms also intersect with the study of dark matter and dark energy, mysterious components of the universe that remain largely elusive to our understanding. Dark matter, which does not interact with light, influences the structure of galaxies and the universe at large through its gravitational effects. Similarly, dark energy is thought to drive the accelerated expansion of the universe, challenging our comprehension of cosmology and the fundamental forces at play. The interplay between normal matter, and dark energy creates a complex web of interactions that shapes the evolution of the cosmos. As we attempt to reconcile the observable universe with the unseen forces that govern it, we are drawn into a deeper inquiry about the nature of reality and our understanding of existence. This ongoing exploration prompts us to consider not only the physical laws that govern the universe but also the philosophical implications of our findings. As we reflect on the emergence of atoms from nothing, we find ourselves contemplating the essence of creation. The processes that led to the formation of matter are not merely scientific inquiries. They touch upon profound existential questions about our place in the cosmos. If atoms can arise from a vacuum and transform into the building blocks of life, what does that mean for our understanding of consciousness, purpose, and the nature of reality itself? In this context, we must also consider the implications of our discoveries for future generations. The study of the universe's origins and the processes that give rise to atoms has far-reaching consequences for our understanding of existence. As we continue to explore the cosmos, we are not merely seeking knowledge for its own sake. We are engaging in a quest that shapes our identity and our place in the universe. The exploration of how atoms emerged from nothing is a profound journey that intertwines science, philosophy, and the human experience. Through the lens of quantum mechanics, cosmology, and philosophical inquiry, we begin to unravel the intricate tapestry of existence. As we grapple with the implications of our findings, we are reminded of the interconnectedness of all things and the profound mysteries that continue to unfold within the cosmos. The quest for understanding is an ongoing endeavor, one that invites us to reflect on our place in the universe and the nature of existence itself. The journey to uncover the origins of atoms and the universe is a testament to human curiosity and resilience. It challenges us to think beyond the confines of traditional understanding and embrace the complexity of the cosmos. As we venture into the unknown, we carry with us the hope that our discoveries will illuminate the path toward a deeper understanding of ourselves and the universe we inhabit. In embracing the complexities of existence, we foster a sense of unity with the cosmos and a recognition of the shared journey of all beings. The atoms that make up our bodies were forged in the crucible of the universe, a reminder of our intrinsic connection to the stars and the mysteries that surround us. As we continue to explore the question of how atoms came from nothing, we open ourselves to a universe rich with possibility and wonder. The profound implications of how atoms emerged from nothing lead us to consider the philosophical ramifications of existence itself. As we unravel the mysteries of the universe, we confront questions that have preoccupied humanity for centuries. What is the nature of reality? What is the significance of our existence in an ever-expanding cosmos? To explore these questions, we must first delve into the philosophical perspectives that shape our understanding of creation and existence. From the ancient Greeks to contemporary thinkers, philosophers have wrestled with the concept of nothingness. Parmenides famously argued that nothingness cannot exist because to think about nothing is to give it a form, an idea that resonates with modern quantum theories where the vacuum state is not truly empty but filled with fluctuating energy and virtual particles. This philosophical inquiry sets the stage for understanding how something can emerge from nothing, suggesting that nothingness is not an absence but rather a complex state filled with potential. In a similar vein, the concept of ontological nothingness challenges us to think about the very foundations of existence. Ontology, the philosophical study of being, compels us to explore the conditions that allow for the existence of anything at all. The notion that atoms and, by extension, all matter arose from a vacuum filled with quantum fluctuations prompts us to reevaluate the boundaries of existence. What constitutes something, in contrast to nothing? If nothing is filled with the potential for creation, how do we define the boundaries of reality itself? Furthermore, the interplay between science and philosophy becomes evident when we consider the implications of the multiverse theory. According to this hypothesis, our universe is but one of countless others, each potentially having different laws of physics and conditions for the emergence of matter. If true, the multiverse theory redefines our understanding of existence, suggesting that atoms and particles might not be unique to our universe but rather part of a vast tapestry of realities. This idea challenges the notion of a singular origin, inviting us to ponder the implications of infinite possibilities and the nature of existence across multiple realms. As we contemplate the nature of existence, we must also consider the role of consciousness. The emergence of consciousness is one of the most profound mysteries in the universe. How do collections of atoms and molecules come together to create self-awareness, thought, and experience? This question invites us to explore the relationship between matter and mind, highlighting the complexities of understanding how consciousness arises from physical processes. Philosophers and scientists alike have sought to unravel the enigma of consciousness. Theories range from reductionist perspectives, which view consciousness as a byproduct of neurological processes, to more expansive views that consider consciousness as a fundamental aspect of the universe itself. This latter perspective aligns with panpsychism, which posits that consciousness is inherent to all matter. In this view, the atoms that constitute our bodies are not just inert particles. They possess a form of awareness that contributes to the larger fabric of existence. In this light, the inquiry into how atoms come from nothing transcends mere physical science. It intertwines with our understanding of what it means to be alive, to think, and to exist within a universe that is continuously evolving. The exploration of these questions often leads us to the realm of mysticism, where the boundaries of science and philosophy blur. Many spiritual traditions embrace the idea of an interconnected universe, suggesting that all things, including atoms and consciousness, are manifestations of a singular reality. This interconnectedness resonates deeply with the scientific principle of entanglement, where particles can become intertwined regardless of the distance separating them. This phenomenon challenges traditional notions of separateness and locality, suggesting that at the quantum level, everything is fundamentally connected. The implications of entanglement echo in philosophical discussions about the nature of self and the illusion of individuality. If our atoms are entangled with those of the universe, how do we define our identities and our relationship with the cosmos? Moreover, the exploration of atoms and their origins invites us to reflect on our responsibility as stewards of the universe. Understanding that the atoms in our bodies were forged in the hearts of stars instills a sense of reverence for the cosmos and the intricate processes that sustain life. As we grapple with the existential questions surrounding our existence, we are called to consider how our actions impact the world around us and the legacy we leave for future generations. As we continue to explore the origins of atoms from nothing, we find ourselves at the intersection of science and philosophy. The inquiry into our origins serves as a reminder of the profound mysteries that surround us and the interconnectedness of all things. In this expansive view of existence, we are encouraged to embrace curiosity, wonder, and a sense of responsibility for the universe we inhabit. In addition to the philosophical implications of atomic origins, we must also consider the ongoing advancements in science and technology that shape our understanding of the universe. The study of quantum mechanics has revolutionized our perception of reality, challenging classical notions of determinism and introducing probabilistic interpretations of existence. This shift invites us to reconsider the role of the observer in the universe, as measurements and observations influence the behavior of quantum particles. One intriguing aspect of quantum mechanics is the phenomenon of wave-particle duality. Particles, such as electrons and photons, exhibit both wave-like and particle-like behavior depending on how they are observed. This duality has profound implications for our understanding of reality, suggesting that the act of observation itself plays a crucial role in shaping the nature of existence. This observation raises philosophical questions about the nature of reality. Is it objective? Or does consciousness play an active role in defining what we perceive as real? The implications of wave-particle duality extend beyond the realm of physics, challenging us to explore the relationship between mind and matter. If consciousness influences the behavior of particles, what does that mean for our understanding of the universe? It compels us to consider the possibility that our thoughts, intentions, and awareness may have a tangible impact on the fabric of reality. This perspective aligns with various philosophical and spiritual traditions that emphasize the interconnectedness of thought and existence. As we journey further into the cosmos, we also encounter the concept of quantum field theory, which describes the behavior of particles as excitations in underlying fields. In this framework, particles are not viewed as discrete entities but rather as manifestations of the energy fields that permeate the universe. This perspective invites us to rethink our understanding of matter, suggesting that what we perceive as solid and tangible is, at its core, a dance of energy and information. The study of quantum field theory also offers insights into the nature of the vacuum state, often referred to as nothing. While the vacuum is traditionally thought of as empty space, quantum field theory reveals that it is teeming with fluctuations and virtual particles. This understanding aligns with the idea that even in the absence of matter, the universe is a dynamic and energetic entity. In this context, the emergence of atoms from nothing becomes a natural consequence of the inherent properties of the vacuum, challenging our intuitive notions of emptiness. In the grand tapestry of existence, the emergence of atoms from nothing is but one thread in an intricate web of interconnections. As we explore this web, we are drawn into the heart of the universe's mysteries, uncovering insights that resonate with both scientific inquiry and philosophical contemplation. The journey of discovery invites us to embrace the unknown and to cultivate a sense of wonder about the nature of reality. The insights gained from our exploration extend beyond the realm of theoretical physics. They influence the ways we engage with the world and our understanding of ourselves. The realization that our existence is intricately linked to the cosmos fosters a sense of humility and gratitude for the complexities of life. It encourages us to approach the world with curiosity and reverence, recognizing that we are part of a greater whole. As we reflect on how atoms came from nothing, we find ourselves at the intersection of science and philosophy. This exploration challenges us to embrace the mysteries of existence and to cultivate a sense of interconnectedness with all things. In recognizing the profound origins of the atoms that make up our bodies, we are reminded of our shared journey through the cosmos, a journey that invites us to engage with the universe in all its complexity and beauty. As we continue to explore the origins of atoms, we encounter the ongoing quest for knowledge that has defined humanity's journey through the ages. From ancient cosmologies to modern scientific theories, our understanding of the universe has evolved through inquiry, exploration, and discovery. Each revelation builds upon the foundations laid by those who came before us, creating a rich tapestry of knowledge that reflects our collective curiosity. This quest for understanding extends into the future as well. As we continue to probe the depths of the universe through advancements in technology and scientific inquiry, we are likely to encounter new mysteries that challenge our current understanding of existence. The development of powerful telescopes, particle accelerators, and quantum computing will enable us to explore phenomena that were previously beyond our reach, offering glimpses into the fundamental nature of reality. In this pursuit, we are reminded of the importance of collaboration and interdisciplinary dialogue. The study of atoms and their origins intersects with various fields, including physics, philosophy, cosmology, and even art. By fostering collaboration across disciplines, we can cultivate a more holistic understanding of existence, embracing the richness of diverse perspectives. Moreover, the exploration of atoms and their origins invites us to engage with the ethical implications of scientific advancement. As we uncover the secrets of the universe, we must also consider how our discoveries shape the world we inhabit. The responsible use of technology, the preservation of the environment, and the pursuit of knowledge for the benefit of all are paramount as we navigate the complexities of the modern world. In summary, the inquiry into how atoms emerged from nothing reveals profound truths about existence, interconnectedness, and the nature of reality. As we grapple with the mysteries of the cosmos, we are called to embrace curiosity, wonder, and responsibility. The journey toward understanding is ongoing, and each revelation invites us to reflect on our place in the universe and the shared journey of all beings. The atoms that constitute our being are a testament to the intricate processes that shape the cosmos. They are not merely building blocks of matter, they are the remnants of ancient stars and the products of cosmic events that unfolded over billions of years. This realization fosters a deep appreciation for our connection to the universe, reminding us that we are part of an intricate web of existence that spans time and space. Each atom in our bodies carries a story, stories of stellar births and deaths, of cosmic dust gathering into planets, and of life evolving under the light of countless stars. The journey of understanding how atoms emerge from nothing is intertwined with the broader quest to grasp the nature of existence itself. It leads us to contemplate the origins of life and consciousness, raising questions about the relationship between matter and awareness. If atoms can give rise to complex structures and eventually to conscious beings, what does that imply about the fundamental nature of consciousness? Is consciousness merely an emergent property of complex systems, or does it have a more profound, intrinsic connection to the universe? As we explore the evolution of consciousness, we must also recognize the role of evolution in shaping the biological processes that govern life. The emergence of life on Earth can be traced back to simple organic molecules, which eventually evolved into complex cellular structures. The processes of natural selection and adaptation played a critical role in this journey, giving rise to the diverse forms of life we see today. This evolutionary narrative echoes the cosmic processes that produce the elements necessary for life, suggesting that our existence is the result of a harmonious interplay between the universe and the living systems it nurtures. Moreover, the exploration of life's origins leads us to consider the potential for life beyond Earth. As we study the conditions necessary for life to thrive, we recognize that the same atomic building blocks that compose our bodies may exist in other corners of the universe. The search for extraterrestrial life has gained momentum in recent years, with missions exploring the icy moons of Jupiter and Saturn and the possibilities of life on Mars. These endeavors not only deepen our understanding of the cosmos but also raise profound questions about our place in the universe and the potential for interconnectedness with other forms of life. The quest to understand how atoms came from nothing also intertwines with the study of dark matter and dark energy, mysterious components that make up a significant portion of the universe. Dark matter, which does not emit light or energy, is believed to influence the structure and behavior of galaxies, while dark energy is thought to be responsible for the accelerated expansion of the universe. Together, these enigmatic forces challenge our understanding of the cosmos and underscore the limits of our knowledge. As we continue to probe these mysteries, we are reminded of the vastness of what remains to be discovered and the potential for new revelations that could reshape our understanding of existence. In addition to the scientific pursuit, the exploration of atomic origins evokes a sense of wonder and imagination. The story of how atoms emerge from nothing is not just a tale of physics and cosmology. It is a narrative that inspires creativity and artistic expression. Artists, writers, and musicians have drawn upon the mysteries of the universe to create works that resonate with the human experience, bridging the gap between science and art. This interplay fosters a richer understanding of existence, reminding us that the quest for knowledge is not confined to the realm of academia but is woven into the fabric of human expression. As we reflect on the relationship between atoms, consciousness, and existence, we encounter the potential for a new paradigm of understanding. The emergence of interdisciplinary approaches that integrate science, philosophy, and art encourages us to embrace the complexities of existence. By weaving together diverse perspectives, we can cultivate a holistic understanding that honors the intricacies of the universe and our place within it. Furthermore, the exploration of atomic origins invites us to confront existential questions about purpose and meaning. As we seek to understand our place in the cosmos, we grapple with the significance of our lives and the impact we have on the world around us. The recognition that we are composed of stardust and part of a larger cosmic narrative imbues our existence with a sense of responsibility. We are stewards of the Earth and its ecosystems, tasked with preserving the delicate balance of life for future generations. In conclusion, the inquiry into how atoms emerge from nothing unfolds as a journey through science, philosophy, and creativity. The interplay of quantum mechanics, cosmology, and evolutionary biology enriches our understanding of existence and invites us to ponder the mysteries that lie beyond our current knowledge. As we explore the profound connections between atoms, consciousness, and the universe, we are reminded of the beauty and complexity of life. This journey not only deepens our appreciation for the cosmos but also compels us to engage with the world around us with curiosity, humility, and a sense of interconnectedness. Ultimately, the story of how atoms came from nothing is a testament to the human spirit's quest for understanding. It encapsulates our desire to explore the unknown and to find meaning in our existence. As we continue to unravel the mysteries of the universe, we are reminded that our pursuit of knowledge is a collective endeavor, one that transcends individual perspectives and unites us in our shared journey through the cosmos. In this exploration, we find inspiration and hope, a reminder that, in the vastness of existence, we are not alone. We are part of a grand narrative that encompasses the unfolding story of the universe. As we embrace this narrative, we invite a sense of wonder and curiosity to guide our exploration. The questions surrounding the origins of atoms and the nature of existence will undoubtedly continue to evolve, but they serve as a reminder of the profound mysteries that define our lives. The pursuit of knowledge is not merely an academic exercise, it is an expression of our humanity, an acknowledgement of our shared journey through the cosmos. With every discovery and revelation, we come closer to understanding the intricate tapestry of existence that binds us all. This journey toward understanding is ongoing, and each revelation invites us to reflect on our place in the universe and the shared journey of all beings. As we delve deeper into the mysteries of how atoms came from nothing, we are not only exploring the origins of matter but also the very essence of existence itself. This profound inquiry urges us to embrace the unknown, cultivate a sense of awe, and engage with the world in all its complexity. In doing so, we honor the interconnectedness of all things and celebrate the wondrous journey of life that unfolds in the cosmos. Thus, the exploration of how atoms emerged from nothing becomes a reflection of our collective curiosity, a quest that spans cultures, disciplines, and generations. It is a journey that invites us to ponder the nature of existence, the origins of consciousness, and the mysteries that continue to elude our understanding. As we navigate this intricate tapestry of knowledge, we are reminded of the beauty and complexity of life itself, and the responsibility we share to explore, understand, and care for the universe we inhabit. The atoms within us tell a story of resilience and transformation, of the cosmos' ability to create from the void. This story invites us to reflect on our own journeys, our connections to one another, and the legacy we wish to leave behind. As we contemplate the origins of our existence, we find not only answers but also deeper questions that challenge us to think critically, to wonder profoundly, and to live intentionally. The story of how atoms came from nothing is a celebration of curiosity, a reminder that the quest for knowledge is a fundamental aspect of being human. As we continue to explore the mysteries of the universe, we engage in a dialogue with existence itself, weaving together the threads of science, philosophy, and creativity to illuminate the path ahead. The journey is far from over. It is merely the beginning of a deeper exploration into the fabric of reality, a journey that invites us to embrace the wonders of the cosmos and our place within it. The exploration of how atoms emerged from nothing has also led to significant philosophical debates surrounding the nature of reality. At the heart of this inquiry is the question of whether the universe is inherently deterministic, or if randomness plays a crucial role in the unfolding of events. Quantum mechanics, in particular, has challenged classical notions of determinism, suggesting that at the quantum level, events may not be strictly predetermined. This has profound implications for our understanding of causality and the nature of existence itself. One of the key principles of quantum mechanics is the concept of superposition, which posits that particles can exist in multiple states simultaneously until measured or observed. This phenomenon raises questions about the role of the observer in the universe. Does the act of observation collapse the wave function and determine the state of a particle? Or is the act of measurement merely one aspect of a broader reality that exists independently of our perception? These questions delve into the philosophical implications of quantum mechanics and how they intersect with our understanding of existence. In addition to superposition, the principle of entanglement further complicates our understanding of reality. Quantum entanglement describes a phenomenon in which two or more particles become interconnected in such a way that the state of one particle instantaneously influences the state of another, regardless of the distance between them. This phenomenon defies classical intuitions about locality and causation, challenging our assumptions about the nature of reality. The implications of entanglement extend beyond quantum physics, leading to discussions about interconnectedness and the fundamental fabric of the universe. As we grapple with these philosophical questions, it becomes clear that the quest to understand how atoms came from nothing is not solely a scientific endeavor. It is a deeply philosophical one. It invites us to examine our assumptions about reality, existence, and the nature of consciousness. The interplay between science and philosophy enriches our understanding of the universe, providing a broader context for the questions we seek to answer. Moreover, the journey of understanding atomic origins intersects with the exploration of time itself. The emergence of atoms and the formation of matter mark a significant chapter in the history of the universe, raising questions about the nature of time and its relationship to existence. Time, as we perceive it, is intricately tied to change and the evolution of matter. The unfolding of events in the universe is a continuous process, and the passage of time serves as a framework for understanding that process. The concept of time is also challenged by the theory of relativity, which suggests that time is not a fixed entity but is relative to the observer's frame of reference. This perspective raises intriguing questions about the nature of past, present, and future. Are these temporal distinctions merely constructs of human perception, or do they reflect a deeper reality? As we ponder these questions, we begin to recognize that our understanding of time is intimately linked to our comprehension of existence and the universe as a whole. As we consider the origins of atoms and their relationship to time, we must also explore the implications for our understanding of the universe's ultimate fate. The current consensus among cosmologists suggests that the universe is expanding at an accelerating rate, a phenomenon attributed to dark energy. This leads us to contemplate the long-term future of the universe, including theories about its eventual fate, whether it will continue to expand indefinitely, collapse into a singularity, or reach a state of equilibrium. The fate of the universe ties back to the origins of atoms and the fundamental forces that govern their interactions. The interplay between matter and energy, as described by the principles of thermodynamics and quantum mechanics, shapes the trajectory of cosmic evolution. Understanding these principles is essential for grasping the larger narrative of existence and the future of all matter, including the atoms that make up our bodies. This exploration of the origins and ultimate fate of atoms also leads us to consider the role of human agency in shaping our understanding of the universe. As we continue to probe the mysteries of existence, we have the power to influence our own destinies and the future of our planet. The advancement of technology and scientific inquiry enables us to explore the cosmos in unprecedented ways, from the tiniest subatomic particles to the vast expanses of space. Our technological advancements have opened new frontiers in our quest for knowledge. Space exploration missions, such as those conducted by NASA and other space agencies, have provided us with valuable insights into the nature of the universe. Telescopes have revealed distant galaxies, while particle accelerators have allowed us to probe the fundamental building blocks of matter. These endeavors not only deepen our understanding of atomic origins, but also inspire a sense of wonder about the vastness of the cosmos and our place within it. As we navigate the complexities of existence and the origins of atoms, we must also recognize the ethical considerations that accompany our pursuit of knowledge. The scientific advancements of the past century have brought about profound changes in our understanding of the universe and our role within it, but they also raise questions about the ethical implications of our discoveries. As we unlock the secrets of the cosmos, we must consider how our knowledge can be used for the betterment of humanity and the preservation of our planet. In an age of rapid technological advancement, the responsibility to use our knowledge wisely has never been greater. The exploration of atomic origins and the fundamental nature of existence calls for a conscientious approach that prioritizes sustainability, equity, and the well-being of future generations. As we contemplate the vastness of the universe, we are reminded of our shared responsibility to protect the fragile ecosystems that sustain life on Earth. The narrative of how atoms came from nothing invites us to reflect on our interconnectedness, not only with the cosmos but also with one another. The atoms that compose our bodies are the same atoms that make up the stars, the planets, and all living beings. This realization fosters a sense of unity and compassion, urging us to recognize our shared humanity and the importance of collaboration in addressing the challenges we face as a global community. As we delve deeper into the mysteries of existence, we uncover a profound sense of purpose, a recognition that the quest for knowledge is not an isolated endeavor but a collective journey that binds us together. The exploration of atomic origins and the nature of consciousness transcends disciplinary boundaries, inviting collaboration across fields of science, philosophy, and art. This interdisciplinary approach enriches our understanding of the universe, offering diverse perspectives that illuminate the complexities of existence. The story of how atoms emerged from nothing serves as a reminder of the beauty and intricacy of the cosmos. It inspires us to approach our exploration of existence with humility, curiosity, and an open mind. As we grapple with the mysteries of the universe, we are called to embrace the unknown and celebrate the journey of discovery. Each question we ask leads us to new insights, and each insight opens the door to further exploration. In this endless quest for understanding, we find not only knowledge but also a deeper appreciation for the wonder of existence itself. As we conclude this exploration of how atoms came from nothing, we recognize that the journey is ongoing. The questions surrounding atomic origins, the nature of reality, and the interconnectedness of all beings continue to inspire inquiry and reflection. In this unfolding narrative, we find a celebration of curiosity and a profound acknowledgement of our shared existence within the cosmos. The quest for knowledge is a journey without end, an invitation to explore the depths of existence and the mysteries that lie beyond our current understanding. As we look to the stars and contemplate our place in the universe, we are reminded of the timeless truth that we are all part of something greater, a grand tapestry woven from the threads of atomic origins, consciousness, and the cosmos itself. This realization inspires us to continue our exploration with wonder and reverence, embracing the journey as we seek to uncover the secrets of existence and our role within the vast expanse of the universe. As we continue to unravel the mysteries of how atoms emerged from nothing, we embark on a journey that transcends individual perspectives. It is a collective endeavor that unites us in our pursuit of knowledge, fostering a deeper understanding of existence and our place within the cosmos. In this shared journey, we celebrate the beauty of discovery and the interconnectedness of all beings, reminding us that, in the vastness of existence, we are not alone. We are part of a grand narrative that encompasses the unfolding story of the universe, a narrative that inspires curiosity, wonder, and a sense of purpose in our exploration of the cosmos. The exploration of how atoms came from nothing invites us to contemplate the profound mysteries of existence, urging us to engage with the universe in all its complexity. It is a journey that calls for curiosity, creativity, and collaboration, a journey that reminds us of the beauty of being alive in a universe filled with wonder. As we continue to seek understanding, we embrace the unknown and celebrate the ever-unfolding narrative of existence, a narrative that connects us to the stars and to each other in the grand tapestry of life. As we delve further into the cosmic narrative of atomic origins, we must consider the implications of our discoveries on various scientific fronts. The interplay between physics, chemistry, and cosmology illuminates the processes that led to the formation of atoms and their subsequent role in the evolution of the universe. By weaving these threads together, we gain a more comprehensive understanding of how the simplest building blocks of matter came into existence, and how they interact to create the rich tapestry of the cosmos. The Big Bang Theory, which remains the prevailing cosmological model for the origin of the universe, posits that the cosmos began as an infinitely hot and dense point approximately 13.8 billion years ago. This singularity underwent rapid expansion, leading to the cooling and formation of fundamental particles such as quarks and electrons. In this primordial environment, quarks combine to form protons and neutrons, the building blocks of atomic nuclei. As the universe continued to cool, these nucleons eventually fused to create the first simple atomic nuclei during a period known as Big Bang nucleosynthesis. During the first few minutes of the universe's existence, protons and neutrons began to come together in a process known as nucleosynthesis, leading to the formation of hydrogen, helium, and trace amounts of lithium and beryllium. This process is crucial to understanding how atoms originated from the primordial soup of fundamental particles. The conditions during this era were extreme, with temperatures exceeding billions of degrees Celsius, allowing nuclear fusion to occur. As the universe expanded and cooled, electrons eventually joined these nuclei, resulting in the formation of neutral hydrogen and helium atoms about 380,000 years after the Big Bang. This epoch, known as recombination, marks a significant milestone in cosmic history. For the first time, the universe became transparent to radiation, leading to the release of the cosmic microwave background (CMB) radiation, a remnant of the early universe that we can still detect today. The CMB serves as a crucial piece of evidence for the Big Bang theory, providing a snapshot of the universe in its infancy and offering insights into the conditions that led to the formation of atoms. The emergence of neutral atoms laid the groundwork for the subsequent formation of stars and galaxies. Over the next several hundred million years, regions of the universe began to collapse under the influence of gravity, leading to the formation of the first stars. These primordial stars played a pivotal role in the cosmic evolution by initiating the process of stellar nucleosynthesis. Within their cores, they fused hydrogen into helium and eventually formed heavier elements through a series of nuclear reactions. This process not only produced the elements necessary for the formation of planets and life but also enriched the interstellar medium with these elements, setting the stage for the next generation of stars and galaxies. The life cycle of stars is a remarkable testament to the processes that govern atomic formation. Massive stars, in particular, undergo a series of fusion reactions that create heavier elements like carbon, oxygen, and iron. When these stars exhaust their nuclear fuel, they end their lives in spectacular supernova explosions, dispersing these newly formed elements into the surrounding space. This cosmic recycling of matter enriches the universe and provides the building blocks for future generations of stars, planets, and ultimately life. The understanding of how atoms formed from the primordial chaos of the early universe is deeply intertwined with our knowledge of the laws of physics. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, play crucial roles in the formation and interaction of atoms. Gravity, for instance, governs the formation of large-scale structures in the universe, while the strong nuclear force binds protons and neutrons together within atomic nuclei. Electromagnetism, on the other hand, dictates the behavior of electrons as they orbit around atomic nuclei, giving rise to the chemical properties of elements. The interplay between these fundamental forces gives rise to the rich diversity of matter we observe in the universe today. Each element possesses unique characteristics defined by its atomic structure and the arrangement of electrons around its nucleus. The periodic table serves as a comprehensive catalog of these elements, illustrating the relationships between them and how they interact to form the compounds that make up everything from stars to living organisms. As we reflect on the origins of atoms, we must also acknowledge the role of quantum mechanics in shaping our understanding of the atomic world. Quantum mechanics describes the behavior of particles at the subatomic level, introducing concepts like wave-particle duality and uncertainty principles. These principles reveal that particles do not have fixed positions or trajectories, but exist in a cloud of probabilities until measured. This inherent uncertainty challenges our classical intuitions and invites us to reconsider how we perceive the nature of reality. The wave function, a mathematical representation of the probability of finding a particle in a particular state, plays a crucial role in quantum mechanics. It encapsulates the complex interplay of possibilities that define the behavior of particles. This probabilistic nature of quantum mechanics has profound implications for our understanding of the universe, suggesting that reality is not as deterministic as once believed. Instead, it introduces an element of fundamental randomness into the fabric of existence, raising philosophical questions about causality, free will, and the nature of consciousness itself. Moreover, the application of quantum mechanics to atomic and subatomic processes has led to groundbreaking technological advancements. The development of quantum mechanics laid the foundation for innovations such as semiconductors, lasers, and quantum computing. These technologies have revolutionized our understanding of the world and enabled us to manipulate matter at the atomic level, opening new frontiers in fields such as materials science and information technology. As we continue to explore the origins of atoms and the nature of reality, we are also confronted with the profound implications of our findings for our understanding of consciousness. The relationship between the physical universe and the subjective experience of consciousness is a topic of ongoing inquiry in both science and philosophy. The interplay between atoms, molecules, and neural processes gives rise to the phenomenon of consciousness, raising questions about the nature of self-awareness, perception, and the limits of human understanding. The study of consciousness has sparked debates about the nature of reality itself. Some theories posit that consciousness is a fundamental aspect of the universe, suggesting that it plays a role in shaping reality. This perspective invites us to consider the possibility that consciousness is not merely a byproduct of neural activity, but a fundamental feature of the cosmos. Such views challenge traditional reductionist approaches to science and encourage us to explore the interconnectedness of all things. Furthermore, the exploration of consciousness intersects with the inquiry into the origins of life. The emergence of complex organic molecules from simpler compounds represents a significant leap in the evolution of matter. The question of how life arose from non-life remains one of the most profound mysteries in science. While various hypotheses have been proposed, including abiogenesis and panspermia, the precise mechanisms that led to the emergence of life are still not fully understood. The search for answers to these questions often leads us back to the fundamental nature of atoms and the processes that govern their interactions. The study of the origins of life necessitates an understanding of the chemical processes that occur at the atomic level, including the formation of complex organic molecules, the role of water as a solvent, and the influence of environmental factors. These inquiries not only illuminate the origins of life but also provide insights into the conditions necessary for life to emerge elsewhere in the universe. As we explore the cosmic narrative of atomic origins and the emergence of life, we must also consider the implications for our understanding of the future. The ongoing exploration of the cosmos and our advancements in technology have opened up new possibilities for understanding the universe and our place within it. The quest for knowledge is not merely an academic pursuit. It is a journey that invites us to confront our limitations and embrace the unknown. In this context, the exploration of atomic origins becomes a celebration of curiosity and a recognition of the interconnectedness of all things. It reminds us that our understanding of the universe is not static. It is a dynamic process that evolves over time. Each discovery builds upon the foundation laid by those who came before us, creating a tapestry of knowledge that enriches our understanding of existence. As we contemplate the origins of atoms and the nature of reality, we are reminded of our place in the cosmos. We are part of a grand narrative that transcends individual experiences, connecting us to the stars, the planets, and each other. This realization invites us to embrace our shared humanity and to recognize the importance of collaboration in our pursuit of knowledge. The exploration of how atoms came from nothing serves as a reminder of the beauty and complexity of the universe. It inspires us to approach our understanding of existence with humility and wonder, acknowledging that there is always more to learn and discover. As we continue to probe the mysteries of the cosmos, we do so with a sense of responsibility to protect and preserve the delicate balance of life on our planet. In this ever-expanding narrative, we find a profound sense of purpose. A recognition that our journey of discovery is not just about understanding the universe. It is about celebrating the interconnectedness of all beings and fostering a deeper appreciation for the wonder of existence. Each question we ask opens new doors to understanding, and each insight we gain enriches our collective narrative. As we conclude this exploration of atomic origins, we stand at the precipice of discovery, eager to embrace the unknown and to seek out the questions that challenge our understanding. The quest for knowledge is an unending journey that invites us to delve deeper into the mysteries of existence, to celebrate the beauty of the cosmos, and to recognize our shared role in the grand tapestry of life. In reflecting on the origins of atoms and their connection to the universe, we are reminded that we are all part of a larger story, a story that spans billions of years and encompasses the triumphs and challenges of existence. This narrative invites us to embrace curiosity, creativity, and collaboration as we continue to explore the mysteries of the cosmos and the nature of our place within it. In the end, the journey of understanding how atoms came from nothing is not merely a scientific endeavor, it is a profound exploration of existence itself. It calls us to question our assumptions, to seek out the unknown, and to embrace the beauty and complexity of the universe. As we journey forward, we recognize that the questions we ask and the answers we seek are interconnected, forming a rich tapestry of inquiry that reflects our deepest curiosities and aspirations. The relationship between atoms and the universe also compels us to think critically about the nature of scientific inquiry itself. Science, at its core, is a dynamic process that evolves in response to new evidence and discoveries. As our tools and technologies improve, so too does our ability to probe deeper into the mysteries of existence. This iterative nature of science highlights the importance of skepticism and open-mindedness, reminding us that our current understanding is merely a stepping stone on the path to greater knowledge. In exploring how atoms emerged from the primordial chaos of the universe, we also engage with the philosophical implications of our discoveries. The inquiry into the nature of existence touches upon age-old questions about the origins of life, the nature of consciousness, and the fundamental structure of reality. As we seek to understand the building blocks of matter, we also find ourselves grappling with the nature of existence itself, what it means to be, to experience, and to know. This exploration invites us to consider the potential for life beyond our planet. If atoms and the elements they form are the fundamental building blocks of life, then the universe is a vast ocean of possibilities for life to emerge. The study of astrobiology seeks to understand the conditions necessary for life, examining extreme environments on Earth as analogues for potential extraterrestrial habitats. By understanding how life originated on Earth, we may also glean insights into the possibilities of life existing elsewhere in the cosmos. The search for extraterrestrial life not only captivates our imagination but also serves as a poignant reminder of our shared existence within the universe. The discovery of exoplanets, planets orbiting stars beyond our solar system, has opened new avenues for exploration. Scientists are actively searching for Earth-like planets located in the habitable zone, where conditions may be conducive to life. These endeavors echo the ancient question of whether we are alone in the universe, a question that continues to inspire generations of scientists and dreamers alike. As we probe deeper into the cosmos, we are reminded that the exploration of atomic origins is not a solitary endeavor. It is a collaborative effort that transcends borders and unites humanity in the pursuit of knowledge. Scientists from diverse backgrounds and disciplines come together to share insights, exchange ideas, and tackle the fundamental questions of existence. This collaborative spirit embodies the essence of scientific inquiry and reflects our collective quest for understanding. Moreover, the study of atomic origins also emphasizes the importance of education and public engagement in science. By fostering curiosity and encouraging exploration, we empower individuals to contribute to the ongoing quest for knowledge. Science is not the domain of a select few, it belongs to everyone, and the pursuit of understanding should be accessible to all. Educational initiatives that promote scientific literacy and critical thinking are essential for cultivating a society that values inquiry and embraces the unknown. As we consider the broader implications of atomic origins, we also confront the ethical dimensions of scientific advancement. The technologies and knowledge derived from our understanding of atomic and subatomic processes hold immense power. This power comes with responsibility, the responsibility to use our discoveries for the betterment of humanity and the stewardship of our planet. As we harness the potential of atomic science, we must remain vigilant about the ethical considerations that accompany such advancements, ensuring that our actions align with the values of sustainability, equity, and compassion. The atomic journey also leads us to reflect on the philosophical implications of our existence. In pondering the origins of atoms, we confront fundamental questions about the nature of reality and our place within it. The universe is a vast and intricate web of interactions, and our individual lives are but fleeting moments in this grand tapestry. Yet, Within this transience lies the beauty of existence, a recognition that each moment is a gift, an opportunity to engage with the cosmos and to seek meaning in our experiences. The exploration of atomic origins invites us to consider the interconnectedness of all beings. Just as atoms combine to form molecules and structures, so too do our lives intertwine with those of others. The relationships we forge, the communities we build, and the shared experiences we create contribute to the richness of existence. This interconnectedness serves as a reminder that we are not isolated entities. We are part of a greater whole that transcends our individual experiences. As we conclude this journey through the origins of atoms and the nature of existence, we are left with a profound sense of wonder and curiosity. The quest for knowledge is a continuous journey, and each step we take brings us closer to understanding the mysteries that lie at the heart of the universe. The exploration of atomic origins is not merely a scientific inquiry. It is a celebration of the beauty and complexity of existence itself. We are reminded that our understanding of the universe is an ever-evolving narrative, a story woven from the threads of curiosity, discovery, and exploration. It invites us to embrace the unknown, to seek out new questions, and to engage with the cosmos in a spirit of humility and wonder. The exploration of how atoms came from nothing serves as a testament to the power of human curiosity and the boundless potential for discovery that lies ahead. In this shared journey, we are called to cultivate a sense of stewardship for our planet and a commitment to the pursuit of knowledge. The discoveries we make today will shape the future of generations to come. By fostering a culture of curiosity, creativity, and collaboration, we can continue to unlock the mysteries of the universe and contribute to a brighter, more equitable future for all. As we stand on the precipice of discovery, we are reminded that the quest for understanding is a shared endeavor, a journey that invites us to embrace the wonder of existence and to recognize our interconnectedness with all that is. The story of how atoms came from nothing is a story of possibility, of hope, and of the infinite potential that lies within each of us to explore, to learn, and to create. With this perspective, we invite you to join us in this ongoing exploration of the universe and the profound questions that shape our understanding of reality. Together, let us embark on a journey that transcends boundaries, ignites curiosity, and celebrates the beauty of existence in all its forms. The universe is a vast and wondrous place, and the quest for knowledge is a journey that we can all share, a journey that reminds us of the power of inquiry, the joy of discovery, and the interconnectedness of all life. As we reflect on the origins of atoms and the nature of our existence, we carry forward the legacy of curiosity and exploration that has defined humanity throughout the ages. The story of how atoms came from nothing is not just a scientific inquiry. It is a testament to our capacity to wonder, to question, and to seek understanding in the face of the unknown. In this spirit of exploration, we look to the future with anticipation and hope. The mysteries of the universe beckon us to delve deeper, to push the boundaries of knowledge, and to embrace the infinite possibilities that await. As we continue our quest for understanding, let us celebrate the beauty of existence and the profound connections that bind us all together. As we delve deeper into the origins of atoms and the very fabric of the universe, we must also consider the role of fundamental forces in shaping the atomic landscape. The universe operates through four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces plays a critical role in the formation and stability of atoms, and understanding them is key to grasping how atoms emerged from the primordial chaos. Gravity, the weakest of the four forces, is responsible for the attraction between masses. It governs the motion of celestial bodies and plays a crucial role in the formation of stars and galaxies. In the early universe, gravity began to clump matter together, leading to the formation of the first stars. These stars, in turn, became the forges of heavier elements through the process of nuclear fusion. Within their cores, hydrogen atoms fused to create helium, and as they aged and evolved, they produced heavier elements such as carbon, oxygen, and iron. This stellar alchemy is fundamental to the cosmic cycle of creation, as the elements forged in stars were eventually released into the universe during supernova explosions. Electromagnetism, on the other hand, governs the behavior of charged particles and is responsible for the interactions between atoms. It allows for the formation of chemical bonds, enabling atoms to combine and create molecules. The electromagnetic force is pivotal in the creation of the diverse array of substances that make up our universe, from the simplest gases to the complex organic molecules that form the basis of life. The interplay between electromagnetism and gravity shapes the structure of the universe at both the cosmic and atomic scales, allowing for the emergence of galaxies, stars, and planets. The strong nuclear force is the glue that holds atomic nuclei together. Without it, protons, which repel each other due to their positive charge, would not be able to coexist in the nucleus of an atom. This force operates over short distances but is incredibly powerful, ensuring that atomic nuclei remain stable. It is within these nuclei that the building blocks of matter are forged, making the strong nuclear force essential for the formation of atoms. Conversely, the weak nuclear force is responsible for certain types of radioactive decay and plays a vital role in nuclear fusion processes within stars. It is this force that allows hydrogen nuclei to fuse into helium in the extreme temperatures and pressures found within stellar cores. The weak nuclear force is also involved in the transformation of particles, contributing to the dynamic and ever-changing nature of matter. The combination of these fundamental forces creates a delicate balance that allows for the emergence of atoms from the initial chaos of the universe. The interplay of these forces is also reflected in the life cycles of stars, where the fusion of lighter elements into heavier ones drives the evolution of the universe and enriches the cosmic environment with the building blocks of matter. As we consider the emergence of atoms, we also acknowledge the role of quantum mechanics in shaping our understanding of the subatomic world. Quantum mechanics, the branch of physics that deals with the behavior of particles at the atomic and subatomic levels, introduces a layer of complexity that challenges our classical intuitions. It is in this realm that particles can exist in superposition, exhibiting wave-particle duality, and can become entangled, creating connections that defy classical notions of locality. The principles of quantum mechanics illuminate the processes by which atoms form and interact. Quantum fluctuations, for instance, can lead to the spontaneous generation of particle-antiparticle pairs from the vacuum of space. This phenomenon, known as quantum vacuum fluctuations, reveals that the vacuum is not truly empty but is instead a seething sea of potentiality. Such insights challenge our traditional understanding of nothingness and hint at the profound interconnectedness of matter and energy in the universe. Furthermore, the study of quantum mechanics has implications for our understanding of the fundamental nature of reality. Concepts such as uncertainty and entanglement raise philosophical questions about determinism, causality, and the nature of existence itself. The enigmatic behavior of subatomic particles invites us to rethink our assumptions about the universe and our place within it, blurring the lines between observer and observed. The exploration of atomic origins also leads us to consider the role of symmetry in the universe. Symmetry is a fundamental principle in physics that underlies many natural laws. The concept of symmetry extends beyond aesthetics. It serves as a guiding principle in the formulation of physical theories. In particle physics, symmetries dictate the behavior of particles and the interactions between them. The discovery of the Higgs boson, for example, was a significant milestone in our understanding of symmetry breaking in the universe, as it revealed how particles acquire mass through their interaction with the Higgs field. The relationship between symmetry and the emergence of atoms is a fascinating topic that connects various fields of science, from particle physics to cosmology. The principles of symmetry provide a framework for understanding how the universe evolved from a homogeneous state to the rich complexity we observe today. It invites us to explore the underlying order that governs the universe and to seek connections between seemingly disparate phenomena. In addition to these scientific inquiries, the exploration of atomic origins raises questions about the nature of consciousness and the human experience. As we investigate the building blocks of matter, we are led to contemplate the nature of consciousness itself. How do the interactions of atoms and molecules give rise to complex phenomena such as thought, emotion, and awareness? The relationship between matter and consciousness is a profound and unresolved question that challenges our understanding of existence. The exploration of consciousness invites interdisciplinary dialogue between science and philosophy. Questions about the nature of subjective experience, the mind-body problem, and the origins of consciousness are topics of great interest and debate. As we seek to understand the origins of atoms and the nature of reality, we are also drawn to explore the depths of our own consciousness and the mysteries of the mind. Moreover, the quest to understand atomic origins is a journey that transcends scientific boundaries. It is a narrative that encompasses the realms of art and culture. The wonder and beauty of the universe have inspired countless artists, poets, and thinkers throughout history. The exploration of atomic origins invites us to reflect on our shared humanity and the ways in which we seek meaning in the cosmos. As we navigate this intricate web of inquiry, we recognize that the exploration of how atoms came from nothing is not merely a scientific endeavor. It is a profound journey of discovery that invites us to embrace the mysteries of existence. It is a call to wonder, to explore, and to engage with the universe in all its complexity and beauty. In contemplating the origins of atoms, we also acknowledge our responsibility to care for the planet and the life it sustains. The elements forged in stars and the complex molecules that constitute living beings remind us of our shared connection to the cosmos. As we strive to understand the universe and our place within it, we are called to embrace stewardship for the Earth and to work towards a sustainable future. The narrative of atomic origins is a testament to the resilience of the human spirit and our capacity for inquiry. It reflects our innate curiosity, our desire to understand, and our longing for connection. As we continue this journey of exploration, let us celebrate the beauty of existence and the profound questions that inspire our quest for knowledge. In this pursuit, we are reminded of the importance of collaboration and dialogue. The exploration of atomic origins is a collective endeavor that brings together scientists, philosophers, artists, and individuals from diverse backgrounds. It is through this exchange of ideas and perspectives that we can deepen our understanding of the universe and our place within it. As we stand at the threshold of discovery, we are invited to embrace the unknown and to seek answers to the questions that ignite our curiosity. The universe is a vast tapestry of interconnected phenomena, and our exploration of atomic origins is but one thread in this intricate design. Each question we ask, each discovery we make, adds depth and richness to the narrative of existence. As we conclude this exploration of how atoms came from nothing, we carry forward the legacy of inquiry and wonder that has defined humanity throughout history. The journey of discovery is ongoing, and the mysteries of the universe continue to beckon us forward. With each new insight, we inch closer to understanding the fundamental nature of reality and our place within it. In this spirit of exploration, we invite you to join us in the quest for knowledge and understanding. The universe is a boundless source of wonder, and the story of how atoms emerged from nothing is a tale of possibility, connection, and the infinite potential that lies within each of us. Together, let us embrace the mysteries of existence and celebrate the beauty of the cosmos as we continue to explore the unknown. As we reflect on the origins of atoms and the profound questions that shape our understanding of reality, we are reminded that the journey of discovery is a shared endeavor, one that invites us to engage with the universe, to seek knowledge, and to celebrate the interconnectedness of all existence. The story of how atoms came from nothing is a testament to the power of curiosity, the joy of exploration, and the limitless possibilities that await us in the vast expanse of the cosmos. As we delve deeper into the narrative of atomic origins, we find ourselves compelled to address the implications of these concepts for our understanding of the universe and the very nature of reality. The emergence of atoms from a seemingly empty void invites us to confront the philosophical questions surrounding existence, creation, and the fundamental structure of reality itself. In contemplating how atoms came from nothing, we touch upon the idea of the multiverse, a concept suggesting that our universe is just one of many possible universes, each with its own set of physical laws and constants. This theory posits that our universe, with its particular configuration of atoms and forces, is the product of a unique set of conditions that arose within a vast sea of possibilities. In this framework, the act of creation is not a singular event but rather a continuous process, with countless universes being born and evolving across the cosmic landscape. The notion of the multiverse challenges our traditional understanding of causality and existence. If multiple universes can exist simultaneously, what does this imply for the origins of our own universe? Are the atoms that constitute our reality merely one manifestation of a deeper, more complex structure? The multiverse theory pushes the boundaries of our comprehension and invites us to consider the nature of reality as a fluid, interconnected web of possibilities. Moreover, the multiverse concept also raises questions about the role of observers in the universe. In quantum mechanics, the observer effect suggests that the act of measurement can influence the state of a quantum system. This idea has profound implications for our understanding of reality, as it posits that consciousness may play a role in shaping the very fabric of the universe. If our perception of reality is intertwined with the underlying quantum processes that govern atomic behavior, what does this mean for our understanding of existence and the nature of consciousness itself? As we explore these profound questions, we must also consider the implications of our understanding of atoms on the development of technology and society. The journey of atomic discovery has given rise to groundbreaking advancements in various fields, from medicine to energy production. The manipulation of atomic structures has led to the development of powerful technologies, including nuclear energy, medical imaging, and advanced materials science. The harnessing of atomic energy represents a double-edged sword, offering both incredible potential and significant challenges. On one hand, the ability to tap into the energy released during nuclear reactions has the potential to provide vast amounts of power, offering solutions to pressing energy demands. On the other hand, the ethical and environmental concerns surrounding nuclear energy and weapons remind us of the responsibilities that accompany such advancements. As we contemplate the relationship between atoms and technology, we are also compelled to reflect on the societal implications of our discoveries. The atomic age has ushered in an era of unprecedented change, reshaping our understanding of the universe and our place within it. As we continue to unlock the mysteries of atomic structure and behavior, we must remain vigilant about the ethical considerations that arise from our technological advancements. Additionally, the exploration of atomic origins challenges us to consider our relationship with the environment and the universe at large. The elements that constitute our bodies and the world around us were forged in the hearts of stars, and as such, we are intrinsically connected to the cosmos. This understanding invites us to embrace a sense of stewardship for the planet and the life it sustains. Recognizing that we are made of star stuff, as Carl Sagan famously put it, encourages a profound sense of unity with the universe. It reminds us that our existence is woven into the very fabric of the cosmos, and as such, we have a responsibility to protect and nurture the environment that sustains us. The exploration of atomic origins compels us to consider the long-term implications of our actions and the legacy we leave for future generations. Furthermore, the interplay between atoms and consciousness raises intriguing questions about the nature of existence and the potential for life beyond our planet. The elements that make up life as we know it are abundant in the universe, suggesting that the building blocks of life may exist elsewhere in the cosmos. The discovery of exoplanets and the study of extreme environments on Earth inspire the search for extraterrestrial life, prompting us to explore the possibility that we are not alone in the universe. The quest for understanding the origins of atoms intertwines with our search for meaning and purpose in the cosmos. It invites us to ponder the nature of existence itself and to seek connections between the microcosm of atomic interactions and the macrocosm of the universe. This philosophical inquiry encourages us to engage with the profound questions of our existence and to seek knowledge beyond the confines of scientific inquiry. As we reflect on the origins of atoms, we find ourselves contemplating the nature of time and its role in the unfolding of the universe. The concept of time is deeply intertwined with our understanding of atomic processes and the evolution of the cosmos. In the early universe, time itself may have taken on a different character, influenced by the dynamics of space, energy, and matter. As the universe expanded and cooled, the passage of time began to take on a more familiar form, allowing for the emergence of structures, including atoms, galaxies, and stars. The relationship between time and atomic processes is a fascinating area of exploration, inviting us to consider how the very nature of time is shaped by the fundamental forces and interactions that govern the universe. In this context, we can also explore the implications of time travel and its relationship with atomic physics. While the concept of time travel has long captivated the imagination of scientists and writers alike, it also raises intriguing questions about causality, the nature of reality, and the potential for alternate timelines. The study of time, space, and atomic behavior offers a rich tapestry for exploration, blending science fiction with the frontiers of scientific inquiry. As we conclude our exploration of how atoms came from nothing, we recognize that this journey transcends the boundaries of science, inviting us to engage with philosophical, ethical, and existential questions. The story of atomic origins is a testament to the resilience of the human spirit and our capacity for inquiry. It reflects our innate curiosity, our desire to understand, and our longing for connection with the universe. The quest to comprehend the origins of atoms is a narrative that continues to unfold, beckoning us to embrace the unknown and to seek answers to the questions that ignite our curiosity. The universe is a boundless source of wonder, and the exploration of atomic origins is but one thread in the intricate tapestry of existence. Each discovery, each insight, adds depth and richness to our understanding of reality and our place within it. As we move forward in our quest for knowledge, we carry with us the legacy of inquiry and wonder that has defined humanity throughout history. The journey of discovery is ongoing, and the mysteries of the universe continue to beckon us forward. With each new insight, we inch closer to understanding the fundamental nature of reality and our role within it. In this spirit of exploration, we invite you to join us in the quest for knowledge and understanding. Together, let us embrace the mysteries of existence and celebrate the beauty of the cosmos as we continue to explore the unknown. The narrative of atomic origins is a reminder that we are part of a larger story, one that connects us to the universe and to each other. As we conclude this exploration of how atoms came from nothing, let us carry forward the spirit of inquiry that has propelled humanity throughout history. The story of atomic origins is a testament to the power of curiosity, the joy of exploration, and the limitless possibilities that lie within the vast expanse of the cosmos. Together, we can continue to unravel the mysteries of existence and celebrate the beauty of the universe we inhabit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.